All right. So good evening, everyone, or good afternoon, I guess, if you're on the West Coast. My name is Megan Roulard, and we are now embarking upon our 8th week of working through Kepler's new astronomy. Just finishing, of course, a month working with Ben through part 2. And my idea, based on looking at part 3, sort of how it's organized, is to do part 3 in 2 parts. So what we're going to cover today is looking at the material in chapters 22 to 31, and then next week to look at chapters 32 through 40. And there's a definite idea, sort of 2 distinct ideas, but part of the overall idea of part 3. It was very helpful. Could have been better, but 4 people submitted their homework. There's obviously more, more would be better, but I think based on last week, that's like a 400% increase. But that was very helpful, actually, because I realized going through it, it's helpful to know in advance what people are having trouble with, what people are understanding more easily and more with more difficulty. So that was helpful. So part 3 is a lot of fun, and I've actually had, it's been, when I first worked through the new astronomy, it's been something like 8 years. That sounds really wild. We didn't have a website. We read through the whole thing, and it's been very fun for me to actually go back through part 3, and can say there's definitely a lot of surprises, especially if we just finished part 2. In a certain sense, you could maybe say the end of part 2. I mean, what more could you want? Kepler, he has his vicarious hypothesis. He shows what's wrong with it. He throws out the assumptions that have existed in astronomy for hundreds of years. The assumption of circular orbits, uniform motion. He just he gets rid of that. Things seem pretty clear. In accord with what how Kuza thinks. Things seem great. And then part 3 starts, and you're immediately confronted with, I would say, definitely some shockers, based on what you might have thought you had concluded at the end of part 2. So we're going to get right into some of those surprises today. So just to start, so what Kepler says about part 3 is he says he's now returning to the investigation of the second inequality. So I want to ask people, maybe don't cheat reading the screen behind me, but if anybody wants to, probably can't see it that well, or maybe I'll block it out with my arms. If anybody wants to say what you think the second inequality is, go ahead, because that's what we're investigating in part 3, and I know from part 1, it is actually a challenge to get what these 2 inequalities are. So if anybody wants to volunteer what they think it means that in part 3 we're going to investigate the second inequality, go ahead. Don't all speak at once. Here. I'll give you the answer. It's right in the title. Okay, now I got to do this. Switch the screen. Okay. So part 3. The title of part 3 is, he gives you the answer right there. Investigations of the second inequality, that is, of the motions of the sun or the earth, or the key to a deeper astronomy, wherein there is much on the physical causes of the motions. So that's pretty clear. Thus far we've been looking a lot at the motion of Mars, you know, against the background of the fixed stars. Been focusing a lot on Mars, and now we are, and Mars's motion, you know, we've been using these observations at opposition, so it's really a simplified motion of Mars. The second inequality deals with the motion of Mars still, but it's as tied to the motion of the Earth or the motion of the Sun, which, you know, we removed the second inequality with a lot of what we were doing in part 1 and part 2 by using these observations at opposition. So we were able to simplify things looking at Mars. But so now we're going to return to how the motion of the Earth or how the motion of the Sun factors into this picture that we're developing. Switch it back here. So yes, if people didn't notice, and this gets to our next point, the name of this class is the equant. Again? Okay, so that is, of course, the shocker at the beginning of part 3. Is, you know, we seemingly ended part 2 dispensing with these assumptions, and here they are again in part 3. What happened? Did Kepler have, you know, was he struck with a bout of amnesia? Did he get counter-organized? Did, you know, what happened? I mean, why did he reintroduce these assumptions that he had seemingly, namely and specifically in part 3, this assumption of an equant, of this point of uniform motion? Why is this rearing its ugly head right after the conclusion of part 2? So I will say I got from the homeworks people did submit, and, you know, if people read the article that Jason wrote on part 3 called, I think it's called Kepler's Paradox Will Return to the Equant, you maybe weren't too freaked out by this, and I got the sense from the homework people had a sense of why Kepler was doing this. So let's just look at what he says. If anybody really has been so overcome by shock that the equant is part 3 is in part 3, you know, feel free to say something, but I'm going to try to clarify it here. Okay, one sec. So already we had a sort of a hint from Kepler earlier in this book, but also going all the way back to the Mysterium about what he thought about the equant. He actually did think about this differently than, you know, someone like Ptolemy. He never thought about it. You know, I think the name of Jason's article is something like "The Paradox Will Return to the Equant: Physics, Not Statistics," something like that. So in chapter 4 of the New Astronomy, Kepler says the point of the equant is nothing but a geometrical shortcut for computing the equations from a hypothesis that is clearly physical. Right? So that's, you know, that's his point, and people's answers reflected that. I mean, Kepler never thought that the equant was something in and of itself. He didn't think it was, you know, as we went through in part 2, he didn't think it was true, but I mean, there's a reason that people were using it, and they were clearly not conscious of that, but it's because it's a shadow of a physical principle. It's a certain way to approximate it. But Kepler's focus is, of course, on that physical principle, what that is. So Kepler, so again, that's from chapter 4. Just some, what Kepler says about this equant. But even going back to the Mysterium, Kepler says the following: he was already in the Mysterium because, as we've already seen, and I know there actually was some unclarity about this, and we can keep talking about it. We've encountered this idea of a bisected eccentricity. We have the center of the orbit, and then on either side of it you have the sun, and you have the equant. And people had used this, and Kepler was using it also. But so back to the Mysterium Cosmographicum, Kepler had, I think, a chapter on this. The title was something like, "What's the physical cause of the bisected eccentricity?" In a sense, what is the cause of this equant? So in the Mysterium, Kepler said, in chapter 22 of the Mysterium Cosmographicum, when I was giving the physical cause of the Ptolemaic equant, or of the Copernican Tychonic second epicycle, I raised an objection against myself. If the cause I proposed were true, it ought to hold universally for all planets. So he has more on what he actually thinks this cause is, which I think we have a sense of, which has to do with the actual sun. But anyhow, he's making the point that the Earth was an exception to this requirement of having an equant, of having an eccentric equant. The Earth hadn't required this. And in terms of Kepler thinking about a universal cause for the motion of the planets, it was a little bit troubling that the Earth seemed to not require this equant, that everybody thought if the Earth has a point of uniform motion in its orbit, it's its center. It doesn't have an actual equant. It just moves, it's a circular orbit. It moves uniformly around its center. So Kepler decides to basically leave this as an open question. He says, really, and it is the case that as people encountered later, later on in part 3, there's an explicit chapter which addresses the fact that it's not so easy to observe the Earth. So there is a reason why observations of the Earth and things about the Earth's orbit were actually more unclear. So Kepler sort of accepted this. He said, okay, we'll let astronomers try to figure this out. I'm going to leave it as an open question for now. But Tycho Brahe confirmed Kepler's doubts, and he said this for him, this was significant. In a letter, and Kepler cites this letter in chapter 22, he cites a letter from Tycho from 1598, where Tycho says, the annual orb according to Copernicus, or the epicycle according to Ptolemy, does not appear always of the same size in comparisons made to the eccentric, but introduces a perceptible alteration. So what they had noticed, and what Kepler will deal with here, is that in order to meet this condition or requirement of having the point of uniform motion be at the center, in order to meet that requirement, the actual size of the orbit appeared to change. Like it would, I don't know, it would sort of, it would oscillate. It would something that was clearly strange. So Kepler already had this question. It's interesting that it came up simply based on observational astronomy. There's sort of a problem. We try to have the Earth's center of uniform motion, point of uniform motion at the center. The orbit appears very unstable. Kepler, already having thought about this from the standpoint of figuring out a universal cause for the motion of the planets, and being a little perturbed that the Earth didn't seem to fit. So this is what he wants to address here. And I think, you know, that sort of lessens the blow of the shock. Now this was in the homework first question. Nobody, you know, it was sort of an add-on thing. Nobody really answered about it. But the other surprise in part 3 is Kepler brings back something else he had seemingly refuted, which is the mean sun. Now, more could be said about this, but what Kepler said, because using the mean sun is actually somewhat central to what he's actually trying to prove about the Earth. But what Kepler himself says is, I'm going to start off, and as people you know, notice if you work through the chapters, he doesn't use the mean sun for the entirety of part 3. But when he's trying to make this point at the beginning, which is a significant point about the orbit of the Earth, he says he's going to use this. And what he says is, I'm going to use the mean sun, lest someone think my innovation in using the apparent motion of the sun is implicated in this matter. He wants people to focus on what he's saying about the orbit of the Earth and not to be able to use the excuse that, well, somehow, you know, it has to do with his use of the apparent sun, which is also this new thing he's trying to introduce. But he only does this for a couple chapters. One sec here. And I'll let people know, I have this Google presentation. I want to go through really each of the chapters. And what I can do, which I thought might be useful for people, is I can send this to people. I can share it with you, and it can sort of serve as notes. So you can look back at it. So I'll do that after the class. All right. So let's go on to Kepler's first proof. How is he going to prove that the Earth has an equant? Which, meaning that, how is he going to prove that the center, that the point of Earth's uniform motion is not at its center? And I think this proof is really cool. I like it because it's very simple. I think it's really very clever. And this is one of the homework questions. I'm going to show you how I proved this. I like it because it's making a really important point using a very simple idea about basically setting something up where you have triangles that have to be similar if the Earth's equan's at its center, and they're not. So similar to what he's done before, he sets something up, and he knows exactly how to set it up to prove his point and to disprove what he wants to disprove. So this is a little awkward. I could here. I'll just show people right here, since you can see that. It's not backwards for them, is it? Anyhow, okay, so this is Kepler's first proof that the Earth's point of uniform motion is not its center. Okay, so we have this diagram over here. He's selecting very specific observations. Actually, one particular observation of Mars, this point M at the top, viewed from two very specific positions of the Earth, both situated at, either point of the line of apsides, and where the angle between the line of apsides and Mars, those angles are going to be the same. So that's his requirement. So the angle at big E and the angle at little e, those are the two positions of the Earth. Those are going to be the same. Okay, that's part of how he's selecting what he's selecting, that requirement. Then he has these other angles which are the same, which this was a homework question. Some people got this, some people didn't. The angle of commutation, which is an angle formed at the center, or at the sun, in this case, the mean sun, between the Earth and Mars. Now, I'm imitating here what he did in his diagram. Those angles are not actually 90 degrees, but he does get them to be the same. They're something like they're like 67 degrees or something. But for ease of, I guess, visualization, I think he has them as 90. But it doesn't really matter. The point is just that they're the same. Okay, so based on that, he can actually make a pretty cool proof, because those triangles, you know, they should be similar, right? They have, if C is the center, the distance from big E to C and C to little e, those distances should be the same. The distance from C to M, they're both going to share that. They're sharing that side, so that distance is the same. The angles of commutation are the same, and the angles at the Earth, from the Earth to the center and the Earth, you know, the Earth to the line of apsides and the Earth to Mars, those angles are the same. So then I sort of extracted these two triangles here. So basically, there is those two triangles, based on what we know, they should be similar triangles. We know all of the angles except for one, but we should be able to conclude, based on how many other things we know about the triangle, the fact that they have two similar sides and two similar angles, the angle at the top should be the same. The angle at M, the angle at Mars. So it's angle CM big E and CM little e. Those should be the same. And what he finds out, he finds what those angles are, and they're not the same. In fact, they're about a degree different. This one is about 38 degrees, the top. Oop. And this one's about 37 degrees. So that's a pretty, I mean, that's a degree. You know, we're dealing with degrees, minutes, seconds, and caring about minutes. And these things are an entire degree off. So I think that's a pretty cool proof. So the fact that those angles are not equal shows that this idea of the equant being at the center, which this construction was based on, that's in question now for the Earth. So a couple people submitted this, drawings of this. There were generally, people seemed to be pretty clear on how he was doing this. I really like it because it's proving an important point, but it's pretty simple because it's just with similar triangles. If anybody wants to say anything, if anybody wants to speak up, if you're really unclear about why this is even here and what point it's making, go ahead. But basically, the other thing about this first part of part 3 is every chapter he's proving the same thing. He's doing all sorts of different proofs. So we're not necessarily going to move away from this. But yeah, go speak up if you have questions.
I had a question. I know you're both triangles here. Where
I can't really hear you.
Can you hear me?
Now I can.
Okay, so those two triangles you drew right there, like C, is a little square there, right? Are you indicating that that's a 90-degree angle?
Yes. Yeah, right here?
Yeah.
Yeah. He says he showed them in the diagram as being 90 degrees. Right? This is like a construction that's basically right. I've separated these triangles out, but this is basically what he has in the chapter, The angles, he said ideally they would be 90 degrees. I think also just to make it easier to show. They're not, but he gets them to be the same. And since this proof is about similar triangles, that's really what matters, is the fact that they're the same. I forget, they're actually like 60, somewhere over, between 65 and 70 degrees.
But I just make sure that, so if they don't have the box, then they're not 90-degree angles. Right?
Yes, that's the way of showing a 90-degree angle. But you can imagine, if I didn't have the box, I would still, indicate that they were the same angle, and it wouldn't actually change anything about that proof. That proof just depends on them being the same.
Okay.
And, yeah. I really like that proof. Similar triangles are powerful. All right. So unless there's anything pressing, let's move on. Because as I said, we're just going to keep proving this and reproving it and proving it differently. He really, yeah, he double, triple, quadruple checks his work here. Because he's making a significant point. I mean, people thought that the Earth had a perfectly circular orbit moving uniformly around its center. And he's saying, no, the Earth has an eccentricity. So that's the subject of the next chapter. So he takes what he does here. He moves on to chapter 23 and says, okay, I'm going to use the fact, actually going to use these angular values that were supposed to be the same but that were different. And he says, I'm going to actually now use those to figure out what the Earth's eccentricity should be. One sec here. So, let me show you this. So, yeah, and he does go through this, and I am going to actually go through with you guys a trigonometric proof that I did, but I'm not going to do this one because it was a little bit, it's a little more involved, and we have to get through some stuff. So he uses the angles that he found, the ones that should have been the same. He determines what the eccentricity of the Earth would be, and he finds that it would be about 1800. That's half of this bisected eccentricity. So he says, and just to go through this again, because somebody actually did say that they weren't clear about what the bisected eccentricity was, and I should have drawn it, but so the full eccentricity for any planet would be the distance between its equant and the sun. So that's the full eccentricity. The bisected eccentricity, which really seems to work the best and different people use, is you have that distance between the equant and the sun, and the actual center of the orbit is directly in between. So on either side, you have, right, so if for the Earth, Kepler thinks the full eccentricity is 3600, half of that is 1800. That being the distance from the center to the equant, or the center to the sun. So he says, right, it's pretty cool. Just based on this simple thing he set up with similar triangles, he's able to pretty quickly say what he thinks the Earth's eccentricity is. So a couple people were also confused about this question I had comparing what he got to today. I probably could have given a hint, but I was just so excited that it's actually so close to what it is today. So one way to quantify this eccentricity is to take 1800 divided by this magnitude he keeps using for a planet's radius, divided by 100,000, you get 0.018. Today we know the Earth's eccentricity is 0.016. Not bad, Kepler. That's really small, though. And you'll see that's very small. Mars's eccentricity is about 5 times this, from what I know. All right. So we're going to keep on proving this and reproving it. And, you know, my idea for this part is really, and I do know, you know, on the website, there's not animations for every chapter here. There's animations for chapter 22, 23, not animations, those are diagrams, 24, which we're going to look at. And then there's nothing until chapter 29. So what I want to do, though, is, you know, again, we don't have time to go through absolutely everything, but I want to make sure that, you know, people at least have a sense of the necessity or the reason for each chapter, because there's got to be a reason, right? Otherwise, you wouldn't need the chapters. Okay. So this next chapter is pretty cool. It's a cool idea. People seem to have fun with this. It's the idea of, and it's in the context of just continuing to prove and reprove his point. But he's doing it by, you know, he's watching the Earth from Mars. So what he's going to do here, it's a little more elaborate, because what he's doing is he's using, here, I'll show you this just so you can read. Oopsies. Sorry. Okay, and we are going to look at the website for this. And, oops, sorry. And I'm going to go through a little geometric proof, which I would have given as homework, but, or I should have, but I didn't want to give it to you before I did it myself, and I only had time to do it today. So chapter 24, he's watching the Earth from Mars. So he's now using a series of different Earth positions as seen by Mars after one Mars year. They don't need to have the same specific locations as in chapter 22, right, where it was really these very specific positions on either side of the line of apsides, which was useful for what he's trying to do. But you know, we know Kepler; he's a rigorous guy. So he's not, you know, he never wants anybody to say, well, you know, what if? He wants to make sure that it's clear that he's making a general proof. So he keeps varying how he's proving it, which is actually a pretty important method to have. So they don't have to have the same very specific locations, and he's going to use 4 observations now, whereas he had used, like in that one, only 2. There were only 2 Earth positions. So the center equant assumption is employed here. He uses this equal times equal angles thing by saying that observations separated by the same amount of time are also at same angles from one another. So he uses this in the construction. And what he's trying to get at here is he's trying to, now he's going to show, right, so he had this construction at the beginning with similar triangles. He used the angles he found to show that Earth had a specific eccentricity. Now he's actually going to try to show that the distances, he's going to get a series of distances from this supposed, you know, central Earth equant, right, its point of uniform motion at its center. He's going to get a series of distances from that point to the Earth, right? And of course, if the orbit, if you know, you would assume if that were the case, if that's the center point and you're tracing distances to the orbit, they would all be the same. And so what Kepler does here is he gets a series of distances and shows that they are different. These are the distances, right, shown on the screen here. You can find, I was going to write the page number, But he has these 4 distances, which you can see they're all, they're all different, and, they're not different by, I know it can be hard to conceptualize the orders of magnitude here, but, you have 66,700, 67,400, 67,700. These aren't off by like 1 or 2. They're off by hundreds. So these series of distances aren't the same, and were the equant at the center, they would be. So let's just look at the website just to see Jason's animation of how this is set up, because it's cool. 1 second. Pull up the website. Yeah, so that's just, in terms of your question, Ray, this is that construction. So you see these angles here. Whoops, they're 90 degrees. The way he shows them there. This just shows the, might as well look at the Earth diagrams. This is useful for people to go through. This is, again, chapter 23. Same thing, using the different angles, trying to get the actual value of the eccentricity. But what I want to look at is chapter 24 here, watching the Earth from Mars. So we have, this is his little construction. People can see you have the fixed Mars. So it's in red, the red dot over there. It's continuing to return to the same position after 687 days, so Mars year. And of course, the Earth is at different positions because the Earth doesn't have the same year. And so then he's going to find the distances, the distances from alpha theta, oh my gosh, my Greek letters, alpha zeta, alpha epsilon, alpha, I can't remember the other one. So he's going to find those distances. So here is Jason's cool animation. I'll move my chair, showing how this is generated. So you can see Mars moving around. And every time Mars moves around its full orbit after a year, we see the generation of another Earth position. And so this is what he uses to then do his geometrical proof that these distances from the center of the Earth's orbit, its supposed, central equant to the orbit, are different. And I'm going to go through how he gets one of those distances. Anyhow, it's fun to watch.
Can you hear me?
Yeah. Uh-huh.
It looks like he made those observations during the daytime, if I'm correct. Is that possible?
Looks like he made them during the daytime. They're at
Like
opposition. I think there's still observations that made at opposition. Why do you say that?
Specifically, that first one there looks like.
How can you tell just from looking at this that it was made during the daytime?
That's a good question. It's a 50-50 chance, I guess.
Well, I think. Go ahead.
I don't know. For whatever reason, I thought that it may look like he did it in the daytime, but.
Yeah, I don't know. I think the
one thing in the nighttime, right? Yes or no?
The one thing we do know is up until chapter 27, he's still using these observations of Mars at opposition, which is like that is at a certain time of day because you're trying to get everything lined up. I think it's at, I think it's at sunset or sunrise. Anyhow, let's actually look at how he gets one of these distances. And yeah, and then we'll move on, where he's just gonna keep checking what he's doing, and yeah. But I just want to take a little bit of time with this, since I know you guys have been forced to do law of sines and this kind of stuff. So I figured, I would show you that I know how to do it myself. And I actually realized doing this that I remembered that I never really liked the law of sines as a law, just because I couldn't remember it, and yeah, I actually couldn't remember it, and so I always did things actually slightly differently. I think the law of sines is in here somewhere. Let's see. No, if I put it here. It's going to be easier if I show this to you guys. Okay, so you guys can study this, and we don't have to resolve everything about it. I think the law of sines is probably in here somewhere, but this is a more intuitive way of, and seems to me easier way to show it. So anyhow, this is a proof from chapter 24, and this is, Jason gives this, he gives this example on the website. He doesn't show how it's done, but he gives the example of finding certain distances, finding these distances given what you know. And he uses the example of this particular distance, alpha eta, given the fact that you know certain angles and certain distances. So I just drew this, and I'll go through it, and if people are unclear, you can ask. You also don't have to get totally clear, because I'll send it to you. People can look at it. So the point is, as I said, he's trying to find these distances, and he needs to do it using what you're given. So we have a triangle here, kappa, alpha, epsilon, I think. The values that you know are in pink. So he knows the length, kappa, alpha, the 100,000. He knows a couple angles. He knows the angle at kappa, 42 degrees, 21 minutes, 30 seconds. And he knows the angle at epsilon. So this is, imagine just this triangle sort of extracted from the chapter 24 construction. So the angle at epsilon is 96 degrees, 22 minutes, 14 seconds. So the law of sines, technically, I actually still can't remember it. And again, this is just similar, and it probably is still the law of sines, but I think that technically would be dropping a perpendicular from epsilon to kappa alpha and dealing with those triangles. The way I don't know. I also just wanted to look at this and see what I could, how I would figure it out without looking up the law of sines. So what I did is I dropped the perpendicular. I created this triangle, this yellow triangle. I dropped a perpendicular from alpha. So I created that triangle. It has a right angle. Ray now knows the little square in the corner. And so the length that we're trying to, the Kepler wants to figure out here is alpha epsilon, the one with the question mark. So he wants to know that. So I'm now trying to figure that out in the context of what I know about this yellow triangle. It's the hypotenuse. So these are the steps I went through. So I'm just going to go through it. If people have questions, you can ask. It might be funny to go through on here, and there's still more to go through, but I'll just let people know what I did. So I found the supplementary angle to the angle the 96 degree angle. So the question is, what angle do I add to that to make 180 degrees? So I found what that was, 83 degrees, etc. Okay, so now the yellow triangle, I know it has a right angle. I know now that angle. I can also know one more side. They just have to take a sine. So people can see that the vertical side of that yellow triangle is actually the sine of the angle at kappa, the 42-degree angle. It's the sine of that angle with a radius of 100,000. So I got that value. So some people all know how to do that with your calculator. So I took the sine of that, got what that was, 0.67376. You need to multiply it by the value of the radius, 100,000. So you get 67,000. Oh no, did I write that wrong? 376. I wrote it wrong. That's what it is, though. Sorry. So I get that. Okay, so I wrote that up there. So now I know one more side. So now I have this yellow triangle. I know two of its angles. I know that vertical side. Seems like enough for me to find that question mark length. And it is. So the way I'm going to figure that out is, okay, the length that I just found, 67,376, that's the sine of the angle I found, the supplementary angle. That's the sine of the angle 83 degrees, 37 minutes, 42 seconds. But I need to know, that's the sine of that angle, but with what radius? Clearly you can sort of tell from looking it's not 100,000. So that's what I want to figure out. I can know that length that Kepler wants to find if I set up the following. So this is, I didn't mark it, but the fourth step I have in here. Okay, so one second. Yeah, so that sine, 0.99382, the sine of my 83-degree angle, 83-degree, etc. angle. So the sine of that times what radius times question mark equals 67,376. So I divide 67,376 divided by 0.99382 equals 67794 as the distance from alpha to eta. So let's see what Jason's website has to say about what I did. So that's, you can write it down, that's what I found, 67,794. Let's go back, check my work on against the website. Hey, what do you know? People can see at the bottom of chapter 24, he lists these distances. Okay, let's see. Alpha eta equals 677794. All right. It's always exciting when you do those proofs and get it right. So anyhow, I just wanted to go through that with people. Again, just to show you how I would figure out one of those distances. It's slightly different from just using the law of sines, but it's a little bit more intuitive to me, and probably is technically the law of sines. But does anybody have any questions about that? Or I'll send it to you and you can look back at it. Or did anybody actually try to calculate themselves these distances? I know I didn't make it a homework question, but did anybody try to do that?
No, but I think it would be helpful if you sent that out, and we'll review it as a group next time we work.
Yeah, I'll do that. For sure. Okay. All right, so now we're going to move through a series of chapters, really 25 through, I asked people to read 25. It's a little shorter and easier to handle. I didn't ask people to read 26 through 28 because they're very long. There's a lot of calculations, and I really just want people to get what he's trying to find. Because that's the thing that can drive you mad about seeing pages of calculations, is you can at least approach it more calmly if you know why they're there. What's he trying to do? So that's what I want people to get clear on. Okay, so chapter 25. Okay, so here he begins his process of double, triple, quadruple checking the actual value of the eccentricity, which he had in the homework. I could have asked people what he said it was in chapter 23. I didn't for some reason. I asked people what he said it was in chapter 25. So he's made this statement of what he thinks it should be in chapter 23. 3600 full eccentricity, bisected 1800. So now he's going to double check, and since then, right, then he checked these distances. That was another different way of showing why he was right, really, in proceeding. There's reason to think that the equant wasn't at the center. So chapter 25, he's going to double check the actual value. I'll show people just this little summary. Okay. So he checks the eccentricity in a different construction. He's also checking it sort of against and with the position of the apogee according to Tycho. Now he's also checking it against things that he already knows, right? That's another way. So he finds that it would be about 1530, but and these chapters are sort of funny because he doesn't get it quite right and then says, well, there might be this particular kind of mistake in data that I have from Tycho, and I know that if I correct it in a certain way, I would get closer to 1800. So that's what he says here. Most of you answer this correctly. He says it's 1530. But he says there may be errors from Tycho, and he's gonna do different kinds of. That's okay because he has other proofs in mind. And 1530, if you think of, that's it. This is all still relatively small. Like if you think about, people answered in the homework, if the Earth's eccentricity is 0.016, you're talking about that compared to 0.018 compared to 0.015. I mean, we're dealing with magnitudes that are pretty close to one another. So he does have a statement of, an assertive statement here, a confidence statement that he is, he's going to, it's funny because it's sort of he's making a assertive statement, but he's going to still keep double checking what he does. You can find this on page 323. He says, it has thus been demonstrated that the center of the Earth's circuit is halfway between the sun's body and the point of uniform motion of that circuit. That is that the Earth has a bisected eccentricity. So that is that the Earth proceeds non-uniformly on its orbit, slowing when it recedes from the sun and speeding up when it approaches. Okay, he's confident, but he's still going to, if there's any, any doubting Thomases, they're not going to be doubters anymore. But he is, one way to look at this is he is confident enough now, right, that at this point nobody's going to say, there's, you don't have any, I don't believe you. At this point he's made a powerful argument. He's done it several different ways. So now he's going to reintroduce, this is the main thing about the next chapter, is he's going to reintroduce the apparent sun. So he says next, what he says at the end of chapter 25, moved by those reasons adduced much earlier, so you guys know in chapter 6 above, I measure out the planet's motion by the sun's apparent motion. So that's the point of the next chapter, chapter 26. Okay. One sec. And again, as I said, these next chapters, I didn't ask people to read them because they're pretty intimidating, even to look at. I mean, you're talking about pages of calculations, and you know, ideally it'd be fun. It might not be fun, but it'd be good to actually, you know, go through and follow it. But what I really try to get a sense of looking at them, it's good to at least look at a chapter like that, like chapter 26, and establish in the beginning, okay, what's he trying to find? And then sort of look through the calculations to see if you can at least follow when he's, you know, when he's actually found what he's looking for, as opposed to it just being like a wash of calculations. Like, okay, I know he's trying to get 1800 as the eccentricity, and at least look for that. That's sort of, I think that's an initial way to approach like these chapters. You know, people can go back and do it if you didn't do it already. So, okay, chapter 26. So he's now using he's triple checking now with the apparent sun. He doesn't want people to miss his main point about the Earth's orbit. He's used the mean sun so far in part 3. In part, lest anyone use it as an excuse to doubt him. But, you know, as people should also get the sense, and I was reading just a book which commenting on the new astronomy, and, you know, it's that is what he says. He says, I don't want anybody to think I don't want anybody to doubt me because I'm using the apparent sun. But as the mean sun was, you know, the center of the Earth's orbit, and that's what we're, you know, as it was viewed as the center of the Earth's orbit, he did actually need to use it to prove what he's trying to prove. So it did make sense that he used it if he's going to go back to, you know, the idea of the equant and whether the Earth has the equant, because, you know, the Earth was, because the mean sun was seen as the center of the Earth's orbit. So, but he also said he didn't want to complicate things. So, but we already knew this. We knew he wasn't going to abandon the apparent sun, because he's convinced. He's already said the Earth is moved by the real sun. So in chapter 26, you can find it. I should have put the page number. He gets, it's towards the end. He gets the value 1800 again for the eccentricity, using the factoring the apparent sun into his calculations. And he has this funny quote. There's some great, the one thing about chapter 26, why it's worth looking at, where you can get over being intimidated by the calculations, is he has some very, you know, endearing and funny quotes. So one quote from this chapter is, he says, so, you know, he's introduced the apparent sun. He says, I, to be sure, have laid all my prejudices and preferences out in the open here, so that I am more afraid of appearing importunate than I am of seeming untrustworthy. So then I was thinking of having a homework question be for people to, you know, this might be hard to judge, but have people pick the funniest sentence in these chapters. And I think it's right here. Funniest little side heading he has. You know, these headings he has on the left. In chapter 26, he has this one that says, Ptolemy refuted in passing. So, and as far as why he's refuting him in passing, this is a little bit, again, I can't get into all of this, and people can look at it. It's on page 336, is that basically what he has said about the Earth, right? People know the Ptolemaic system. It introduces huge, ridiculous complications into the Ptolemaic system. It introduces ridiculous. The epicycles have to have really ridiculous, complicated, impossible properties to account for the fact that the orbit, to account for this eccentricity. So essentially, Kepler says, this in and of itself is an indication that, the Ptolemaic, he's obviously showed the equivalence, but there's, he showed the equivalence, but he'll also admit that, some of the systems are more or less complicated. And he says, this just makes the Ptolemaic system, so complicated that I'm not even going to treat it anymore. Right? Thus far, he showed the equivalence, but he'll still then prove things or show them according to each system. And in this chapter, he says, I'm no longer going to even use the Ptolemaic system to prove anything. So he has this funny side heading, Ptolemy refuted in passing, and he says, the quote is, the sun itself, so here, the sun itself, the clearest of truth, will melt all this Ptolemaic apparatus like butter. So as I said, he says he's no longer going to even do proofs in the context of the Ptolemaic system because it's going to be, based on what he's shown about the Earth, it's going to make proving anything with Ptolemy's system far too complicated. So not having fully developed his own theory yet, he says something like, so nobody will want to be in Ptolemy's camp anymore. Half of them will go to Bra, half of them will go to Copernicus, but obviously, he's building his own system. Okay, so that's it. So people can look more, if you want to look more at actually, he does actually go through what the Ptolemaic epicycle, what it has to do. It's on page 336. I just didn't have time to go through all of it, and it probably would have taken a long time to make a pretty simple point. As Kepler said, he's just refuting in passing. Okay, so wrapping up here, we have chapter 27 and chapter 28. So these chapters, I'm not going to say much about them. It's really like quadruple checking, quintuple checking at this point. So what he's doing, put this up, people can see. Oops. So chapter 27, he's using other Mars observations, but they aren't achronical. Now, can anybody tell me what that means? What does it mean if he's using observations which aren't achronical?
It's when they're measured against the fixed stars, when you have a night riser, when something is, when you have, like, let's say, Mars rising in a constellation as the sun is setting, so they're in opposition, so they're taken against the fixed stars?
Yes. So thus far, he's, these observations, they're the easiest, they're most reliable, but he doesn't want to be, he also doesn't even want anybody to say, I imagine that, well, you only prove this with observations at opposition. So chapter 27, that's the point. He's using other observations of Mars that are achronical. As Cameron said, that means that they're not these observations at opposition, which he's he's used a lot so far. He's still satisfied. He still gets about 1800. And this is another funny thing where he says, well, I actually got 1653, but the apogee was questionable. Chapter 28, he uses the assumed eccentricity. So now he's going to take that, he's going to assume it, and check it against a distance which he's supposed to know, right? So it's another way of checking it. And he gets, this chapter, it's like pages of calculations. If you read the beginning, if you want to read through, but focus on, and this is what I did. If you go to page 355, you can see where he says, I get this distance, and this is what it should have been. So therefore, since this was based on my assumption of this eccentricity of 1800, this is a further proof that I'm right. Okay. So wrapping up here, last couple chapters. Okay. So chapter 29 and chapter 30, Kepler now, okay, he's pretty, this issue of the eccentricity is clear. But now, and, you know, this is there's some foreshadowing here of really part 4, where he still has to, you know, what he's done is revolutionary so far, but, you know, he still needs to actually figure out what the shape of this orbit is, and, you know, to be able to forecast where the planet's going to be. He has to actually, you know, figure out the orbit. So in these chapters, he's referenced this before, I think a couple times in the past couple chapters, the idea that, well, you know, because he's still sort of a lot of these proofs, it's still based on the assumption that the shape of the orbit is a circle. So he has now, based on what he's done, he has some improved distances. Chapter 29, he continues to actually get more distances, taking into account this overall correction that he's made. So armed with these improved distances, based on what he figured out about the eccentricity, he starts to, again, ask, what is the shape of the Earth's orbit? Not only is it equant eccentric, but the orbit appears to be an oval, not circular. I'll just put this up for people. And I will show people one thing. So chapter 30 is essentially just a table of distances. And these distances will generate an oval shape. And he's going to, as I said, he's going to return to the oval in part 4. So something I'll show you guys you can play around with. It may not be that much there may not be that much to play around with, but I had found, going through my old New Astronomy stuff, that I had printed out, I'll show you on the website, and I'll show you where Jason animates this oval shape. There's a PDF just of this table, of the distances in this table in chapter 30. There's a PDF of what shape this actually makes. Now, I just thought it would, I remember doing this before and I did it again. Okay, this is an oval, so, I should be able to break out my, ruler and compass and show where it's deviating from a circular path. And it really is so slight that it's actually really even hard to tell if you find the center point and see how much it comes in at the edges. It's super slight. But I'll show you where you can find this and just show people Jason's animation, and then we'll be done soon.
Hey, Megan?
Yes?
Is that because Earth's eccentricity is so small?
Yeah.
The oval's like a circle?
Yeah.
Oh, okay.
So, Jason's not here, but as far as I can tell, this animation here is, hold on one sec. Third line is connected to the blue and the oval path. Okay, as far as I can tell, it's also very complicated how he generates the shape, and I'm not going to go through it. Because it's difficult. You have to take, what you have as distances and figure out at what angle, what's the proper angle corresponding to each distance, and then try to generate a shape. It's not easy. So Jason does animate this here. The oval path, I think Jason's point here is just to show how it's generated. I do believe this is exaggerated, this green oval path. I'm pretty sure that that's exaggerated. And I'm also saying that based on looking at, oh, am I? Yeah, okay. I'm also saying that based on looking at this PDF. So this is what I'm talking about. So people can find this, it's just at the bottom, but this is a PDF of actually like what is, what's the data from chapter 30 showing these distances. So you can print it out. This is what I had done. I found my old paper, print it out, try to see, measure and see what's going on there, and it's practically a circle. You could tell that if you printed that out and did just that. The orbit, it comes in, and it's his point. It's known. It comes in only very, very slightly at the sides. Okay, so just brief word about the last chapter, and then see if people have questions in general, and then we'll wrap it up here. We have this call at 9, and yeah. So the last chapter is funny. I think it's sort of funny because don't need to spend much time on it, but so people remember the very beginning, Kepler says, the person who made me, one of the people who increased my confidence that the Earth had this, that its equant was not at its center, was Tycho Brahe. Now the funny thing is the last chapter addresses, so maybe this is why he didn't try to figure out himself, but so while he expressed this concern, he also had concerns about what would happen if you did give the Earth an eccentric equant, and if you gave the Earth a bisected eccentricity, which that would require. He actually thought, so he thought it needed it, but he was also worried that if he did it, it would show some of his data to be wrong, which is sort of funny. So the last chapter, not the last chapter of part 3, but really in this chunk, is Kepler, relieving Tycho's fears. He says, don't worry about it. I bisected the eccentricity, and he was worried about some of his longitudinal measurements. And he says, don't worry, Tycho. Terrestrial longitude measurements are still, they're still accurate, so don't worry about it. And it is the case that the the type of correction that Kepler was making in this part for the Earth's orbit, I mean, it is so slight, this eccentricity. It ended up being more important for distance measurements than longitudinal measurements, than locating the actual position of something against the fixed stars. So he said, don't worry, Tycho. Earth has a bisected eccentricity, and it's not going to make you look bad. Plus, you were the one who encouraged me that this was the case. So anyhow, that's what I want to cover. That's really half of part 3, and it's really it's a, you'll see as we go on to chapter 32, it's a distinct idea. And now Kepler is ready. He's ready to actually tackle the power that moves all of the planets without exception. So that was the point of these 9 chapters, was making sure that he can just, that he can make his argument for a universal principle which moves all the planets without exception, specifically the exception which had existed up until then, up until he wrote this part, up until the exception with which people had made for the Earth. So now he's double-checked, triple-checked, quadruple-checked. Nobody can say that the Earth is an exception. And he as we'll see, now that he's done with that, chapter 32 through chapter 40, which we'll cover next week, he is going to proceed, he's just gonna go full force with the idea of what the actual physical power is moving the planets and how this actually relates to the body of the sun, how the sun powers the motions of the planets. But you had to get rid of this. There was this little rub, which is that the Earth was an exception. He definitely didn't want anybody to be able to challenge his physical theory with that. So that's what I want to cover. So let's just see if people have questions on anything so far. I know that was a lot. It's a lot of chapters, but it is, as I went through, it is a lot of it's pretty clear he's doing one thing and he's checking his work a lot, which is good to follow. But if people have questions, go ahead.
Yeah, Megan, just a couple questions. Because I was doing the homework and I was kind of thrown off by the whole bisected eccentricity concept.
Yeah, it's weird.
Because, I mean, if you just define it as if you just define the eccentricity as the distance from the center to the equant, and with respect to the equant, and then the distance from the center to the sun, and then if those two are equal, you have a bisected eccentricity. Mm-hmm. That seemed it's simple, but I was having trouble, grasping that simple idea because I didn't really understand why that term would even be used by Tycho and what he calls the ancients, right? The three before him, because they didn't see any significance to the real sun. The sun played no role, as Jason describes it in his paper. They treated the sun as celestial decor. So
right.
So I was having trouble even getting the concept of the bisected eccentricity because they didn't even think. So it just seems kind of like sort of like a meaningless term unless you're Kepler and you're looking at something physical. But it seems like. But anyway, so that put to the side. Just I also wanted to say that the fact that it is bisected, I mean, is a really clear. And it's bisected for all the planets.
Yeah.
It's a real clear indication that not only is there a mathematical regularity that can be found within the orbit, which, as Jason went through in his paper, would reflect a forcible cause which decreases with proportion to the distance moving the planet as it goes around its orbit, but it also points directly to something that the sun would have to be involved in this, because if that relationship always holds, you're going to want to look at the sun if that's there. Anyway, so that's just what I was thinking about on that. But then also I had a question on just and you probably went over it, but I was taking notes, so I probably missed when you were saying it. Just on this oval orbit.
Yeah.
I didn't really understand what he was doing there or why he was doing it.
Yeah.
So maybe if you could just briefly summarize that again.
Yeah, the bisected eccentricity, I agree. When I started looking at this again, I said, that is so weird. And really, if people want to go back also and look at Jason's article on part 2, which I looked at again, the fallacy of the equant, he even has a little, because that was part of Kepler, that was part of the vicarious hypothesis, was And part of why people used it was really, I mean, what are people trying to do? They're trying to get their models to work. And so it seems like a strange, yeah, it just seems like a weird geometrical property of an orbit. And it's really weird to think about it like that. And, you know, Kepler's point, which he says, you know, in the Mysterium, I think chapter 22, maybe it's here, he had a chapter like called "What is the cause of the bisected eccentricity? What's the physical cause?" So that's the thing to keep in mind, and also, you know, why the equant is coming back is it's not just this strange geometrical thing, or if it is for these other guys, for Kepler it's not. Kepler says there's not just going to be some strange geometrical characteristic of the orbit, you know, without a physical reason. My understanding, though, as far as why these guys used it, and I'm hesitating in case I'm wrong, but I'm pretty sure, since it's the distance between, right, the eccentricity, it's the sun, right, sun to the center to the equant. And the bisected eccentricity, the center is, you know, right in the middle of those. I think they were still using the mean sun. I don't think the fact that they had the bisected eccentricity was because they were using the apparent sun. Kepler, of course, you know, does that, and I think that, you know, that's part of what he shows in part 2 is that when you introduce that, you have the bisected eccentricity based on the apparent sun, then it, right, that was like the, you know, the wrench in, then he shows that there's assumptions about these orbits that are wrong when he uses the apparent sun. But
oh, I see. That makes sense. That clarifies it. Thank you. They were, yeah, that makes a lot more sense. I was thinking that even the ancients were using the apparent sun, but no, if they're using the mean sun, then
yeah, I think for the bisected eccentricity they are, and then I think that's part of, you know, what Kepler is doing, how he shows. Yeah, I think that's part of what he's doing in part 2. Pretty sure that's the case, but yeah, in general, his point is, yeah, it is really strange. It is a really strange geometrical property of an orbit, but it's not, you know. If just as that, it would be like, whoa, this is just really weird coincidence. But it's not a coincidence. It's because the planets are all moved by the same physical power. On the oval, I didn't go through in depth how he generated the shape, but you know, he keeps he's gotten. I mean, the very fact of the eccentricity sort of suggests that the orbit, you know, may not be circular. But he also, what he's gotten throughout this part 3 so far, and what he continues to try to generate in chapter 29, is a series is distances. He's a series of improved distances. Based on what he's figured out, and that's what this whole table is, chapter 30, is he has a whole series of new distances corrected, taking into account what he's figured out about the Earth, and he uses sort of it's complicated what he does, and that's why I directed people to just this this PDF of the actual shape that you get from the table in chapter 30. When you take all of those distances and lay them at the angles that he says that you should, he says you get a very slight oval, which is that it comes in very slightly at the sides. And, you know, a lot of part 4 is going to be him, ultimately, you know, he's going to want to figure out the actual shape of the orbit. And so he's sort of, you know, he has to dispel with a lot of assumptions, but he's introducing that here, and it's going to really be the bulk of part 4, which is he's going to bring back the oval, an egg. He's going to, he has to reconcile the shape, right? How does he, and then there's just the shape, not as a geometrical shape, but how does he reconcile a shape that he gets with a hypothesis of a physical cause which could create that shape? That's a lot of what he's going to be doing from here on out. So, on the oval, I would really suggest looking at the website, and if you want to actually see how close the shape is to a circle, print out that PDF. It's pretty slight.
So he's basically just saying that, well, look, based on the calculations of these distances, there's a possibility. We have to consider the possibility that it's not actually a circle, but it could be an oval.
Yeah, and you can see how you could already if the center of uniform motion is not at the center, you could maybe also, I haven't thought this through fully, you could also assume that, well, how is that gonna vary is that not going to cause some variation in the actual shape of the orbit? If the power moving the planet is not at the center, if it's off center somehow. But he also is just getting it from here. He is getting it from distances and figuring out a series of distances and how to lay them at proper angles and see what shape he gets. So, and as people know, that was one of the things that he disproved, along with the equant, at the end of part 2, right? Was the point of uniform motion and circular orbits. So he already has in mind that he's proved that the orbits are not circles. But he's got to substantiate that, and actually having distances which show that help. Positive proof, if you will. Anything else? Well, if you didn't have fun this week, you'll have fun next week. Next week is very playful, I would say. You have to be in a playful state of mind, not the state of mind of a geometer or it's very playful because he's really it's full-on hypothesizing what this physical cause could be, and he throws all sorts of hypotheses out there. Chapter 32, I'll just read you guys from the chapter summary. And this is the name of the next class. He says, when you get to chapter 32, physicists, prick up your ears. Says, for here is raised a deliberation involving an inroad to be made into your province. So that's going to be next week, and it's a little bit different. And for the homework, I posted the homework questions. I did suggest that people actually read all the chapters, 32 through 40, and because it's different what he's doing, it's a little bit easier to read. There's not a whole, with some exceptions. Chapter 32, there's a significant construction in there, as well as chapter 40, but a lot of those intermediate chapters, he's just hypothesizing about light, magnetism, and they're actually fun to read. So I'd encourage people, if you can, to actually read them. And I posted in the folder. Oh, now I'm trying to think. No, did I not do that right? I'm trying to think what you guys can access and what you can't. I was thinking I have missing pages from chapters 33 and chapters 37. I have those. I guess I'll email them to people. For some reason, I thought you guys had access to the. Yeah, you guys don't have access to the actual LPAC Science Google Drive account, so I can email them to you. As far as next week. But are there any more questions? Otherwise, we have this call in about 20 minutes.
I had one more question. In Jason's article, when he's talking about Kepler and his first hypothesis and the mysterium on the physical causes, and he says, I'm not going to look at, I think he talks about bisecting the eccentricity right now, whether he comes back to it later. It's just, one thing is just really funny, the idea of a physical equant, because it's inherently geometrical. And you know, he doesn't try to get constructions to work for observations based on sense perception. But he's looking at physical causes, and then he plays out in a Socratic dialogue type of way of the equivalence of hypothesis to show the absurdity of where they break down. But there's something in there that I was thinking that was pretty wild. Is, do you know what Kepler was thinking when he said this moving spirit, as far as the sun being the mover, that it's something that exists everywhere? In, like, was it like, think, you know, we only knew of the solar system, you know, we didn't know about galaxies. But you know what he was thinking along those lines for the universe?
About the power of the sun?
That he talks about, like, this whirling spirit or something that's everywhere.
Are you saying in the Mysterium?
Yeah.
Did you read that chapter?
No, but I just picked that up from Jason's article. Right.
Yeah, I'm not sure. What I do know is, and you'll see, you know, we'll get into next week, and you know, really, I don't have a lot of answers about it, and neither does he. And so he really, this is exactly what he's trying to figure out. He has this sense that the sun is the mover, but he says, well, how does this, you know, how is it, I know it's a mover, but really, how does it act? What is it? Is it like anything else that we know of? I mean, I forget, he describes it at one point. He says it's something like, you know, akin to the power of the soul. He throws a lot out there in the next part, and so I think I'm not familiar with everything he says in the Mysterium about it, but what we'll see is still, even here, that the chapters which we're going to work on next week, he's really still totally in the realm of operating in the realm of hypothesis about how the sun actually acts on the planets, and he entertains a lot of different ideas. You know, he discusses it in terms of the soul, in terms of light, in terms of magnetism. You know, what can possibly impede this power? You know, is there anything that can make it weaker? Yeah, so, I mean, I don't know, and what we'll see next week is, you know, people are going to have to be, it's fun, but people will have to be loose, because a lot of what he says, you could say, isn't, you know, maybe right. But it's really, I mean, this is the point where he's, you know, he's been creating the new astronomy for the whole book, but, like, this is really it, the point we're at now, which is now he's dismissed with all the bad ideas, and he actually has to generate, now he has to generate a positive concept of what's happening. You know, and what's generating these total shadows, like the bisected eccentricity and the equant, which for him were only shadows. You know, as he said, he never thought that there was any, you know, you're not going to have any cause from being emitted from a geometrical point that things are paying attention to. So, I mean, I don't have anything conclusive to say about it. I think it would be fun to go back and, if anybody wants to share anything next week, it would be fun to go back and read this chapter 22 of the Mysterium. People could share next week.
I'll look at it.
Yeah, that would be great. Okay. Well,
Thank you.
you guys had fun. I had fun. So, yeah, if there's nothing else, we'll continue next week, and I'll send out the missing pages from the next chapters, and I'll send out this little Google presentation I had so people can sort of use it as notes. And do your homework. It'll help make it better. All right. Bye, guys. Thanks.
Bye.
Goodbye.